In this video, we take a look at functions and function notation. So we're going to ask the question, what is a function and how can I see if something is a function or not? The first thing we want to start with is the concept of a relation. In mathematics, a relation is a correspondence between a set of inputs, which we usually call the domain, and a set of outputs, which we call the range. So anytime I have inputs and outputs, I have a relation. So the relation connects inputs and outputs. One type of notation that you could see with relations is what I call bubble notation. Bubble notation for me just means I have a big circular or elliptical bubble around a set called the domain and a big circle or elliptical shape around the set called the range. And then the relation is the arrows between the elements of the domain and the elements of the range. Usually people put the domain on the left and the range on the right so that the arrows go left to right in English because that's how we read English. So here we have the element A in the domain going to the number 2 in the range. The element B goes to the number 1. Also, the element B goes to the number 3. The element C in our domain goes to the number 3. This is a visual of a relation. Now, a lot of times bubble notation takes up a lot of space. So there are other notations for the concept of a relation as well. We have what I call arrow notation and ordered pair notation. Arrow notation oftentimes just lists the input element first and then an arrow pointing right to the corresponding output element. So we saw in the bubble notation that A was sent to the number 2. We'd have A, a right arrow, and then 2. B was sent to the number 1. So we have B, arrow pointing right, sent to the number 1. Here, B is sent to the number 3, B, arrow pointing right, number 3. And then C is sent to the number 3 as well. So C, arrow pointing right, number 3, all separated by commas just so we know that they're not the same things. Sometimes arrow notation will have a big set bracket around it as well, just like the next notation, which is the ordered pair notation. The ordered pair notation has ordered pairs where the input is the first element in the ordered pair and the corresponding output is the second element. So A being sent to 2 would be, as an ordered pair, A, comma, 2. B being sent to 1 would be the ordered pair B, comma, 1. B being sent to 3 would be B, comma, 3 as an ordered pair. C being sent to 3 would be C, comma, 3 as an ordered pair. Once again, the inputs are always the first elements, the outputs are the second elements. And like in this case, I have drawn, or I have typed, I should say, set brackets around the entire ordered pair set. So the bubble notation here obviously took up the entire page. The arrow notation was a little bit smaller. The ordered pair notation was also smaller than the bubble notation. So all of those are just different notations we have for relations. Now we want to look at what a function is. A function is a relation such that any single input can only correspond to one output. So in other words, if I have an input, or if I give you an input, you know exactly where it goes to. So a function is this special type of relation that if I give you and somebody else an input, you both wind up at the same output guaranteed. Now let's look at our previous relation. Our previous relation was not a function because the b was sent to 1 and this b was sent to 3. Because that single input was sent to 2 different outputs, this relation would not be a function. In the drawing, basically what that eliminates is that eliminates having 2 arrows out of a single input. So here we had a single input of B. We had 2 arrows pointing out. That is not allowed. So let's take a look at this example number 1 and determine if these relations, which are all in ordered pair notation, could represent functions or not. Let's look at the first relation. We have the ordered pair 1, 2, the ordered pair 1, 4, the ordered pair 3, 6, the ordered pair 5, 7, and the ordered pair 8, 9. In this relation, we could not, this is not a function because the input of 1 goes to 2 and also the input of 1 goes to 4. So since 1 can be sent to 2 different numerical values, this relation is not a function. Let's look at the next relation. 1 is sent to 2, 2 is sent to 3, 3 is sent to 4, 4 is sent to 2, 5 is sent to 3. This relation, this second relation, is a function. Notice that 1 is sent to a unique value. 2 is sent to a unique value. 3 is sent to a unique value. 4 is sent to a unique value. 5 is sent to a unique value. So the second relation is a function. It's perfectly fine that multiple things got sent to the number 2 and that multiple things got sent to the number 3. That's okay with a function. So that second relation is a function in this case. In ordered pair notation, you see basically what makes a function a function. If I have each input only being represented in one ordered pair, then we have a function. So this is a function, this second relation. This third relation, 0 is sent to 0, 1 is sent to 1, 2 is sent to 5, 3 is sent to 6, 5 is sent to 10. That is a function as well. 0 is sent to unique value, 1 is sent to a unique value. So in other words, we don't have repeated inputs. So this first relation was not a function. The second relation was a function. The third relation was a function in this example. Now, oftentimes, we don't want to write ordered pair notation because we have infinitely many elements in our domain. In the first few cases, we had finite numbers of ordered pairs. What if we have an infinite number of ordered pairs? Or what if we have just infinitely many values in our domain? We can't list them all out as ordered pairs. And oftentimes, if we have infinite domains in our function, we can write the relation as an equation with variables x and y. Our ordered paired solutions to the equations give the corresponding relation or the correspondence relation. So the ordered pairs that make the equation true give the correspondence for the relation. And generally speaking, we let the x values of the equation represent our domain and the y values represent the range. That's not always the case, but that's the usual way to do it. So for instance, let's say we have a relation which is x minus 6y is equal to 10. We can ask, does that relation contain the following ordered pairs? That means when you plug those in, do you get a true statement in that equation? Now remember, x here was representing the input values, y is representing the output. We already said generally in the order pair notation, we always go input first and then output second. That's because, again, as in English readers, we read left to right. So if I'm thinking about for 1, what I would do is I would say x minus 6y equals 10 and replace the x with a 4, replace the y with a, for negative 1. So replace the y with a negative 1 and then simplify. Simplifying the left-hand side gives me 10. The right-hand side is obviously 10. So this means for 1 is in the relation. So that ordered pair is in the relation correspondence. All right, or the correspondence to that. Let's take a look at 2, 3. So we want to figure out whether 2, 3, is in the relation x minus 6y equals 10. So I say x minus 6y equals 10. And then I replace the x with a 2, the y with a 3. And then I simplify both sides of that equation. I would get 2 minus 18, which is a negative 16 on the left-hand side, and then a 10 on the right-hand side. Obviously, that is false. Maybe I should have written in the previous one that that's obviously a true statement. Since it's a false statement, then 2, 3 is not in the relation. You can do that with every single ordered pair. So let's do that with 5, -1. Again, we just write x minus 6y equals 10. And then plug in 5 for the x, plug in -1 for the y. Simplify both sides. 5, that's going to be a plus 6. So we're going to get 11 is equal to 10. That's obviously false as well. So 5, -1 is also not in the relation. (22)(2). Let's check this one out. So again, x minus 6y equal to 10. We plug in a 2 for the y. We plug in a 22 for the x. Simplify both sides. 22 minus 12 is 10. That's a true statement. So 22(2) is in the relation. All right. And you could probably guess that there's going to be infinitely many ordered pairs that make this equation true. And there are. There are going to be infinitely many ordered pairs that make that equation true. There's going to be also infinitely many ordered pairs that make that equation false. So we have a way now of testing whether an ordered pair is in the relation by plugging it in and seeing if the equation gives me a true statement or a false statement. If it gives me a true statement, I know it's in the relation. This correspondence gives me that relation. Let's look at another example. Here is a different correspondence. We have y squared equals 3x. And we ask, does the relation contain the following ordered pairs? 5, -2, -3, -3, 12, -6, and 12, +6. Once again, I'm just plugging in my inputs into X, my outputs into Y, and seeing if I get a true statement. So 5, -2. Be careful when you plug this in because the -2 needs to go on the inside of the parentheses so that the entirety of -2 gets squared and is equal to 3 times 5. Again, plugging in 5 for X and -2 for Y. Be careful that you plug this in because you want -2 quantity to be squared so that you get a 4 on the left-hand side. And this one gave me a 15 on the right-hand side. Obviously, that's false. 4 is not the same thing as 15. So this ordered pair is not in the relation. Let's take a look at -3, -3. If I plug in -3, this is the y value of -3 into the y and square it. Again, I have to make sure that's in parentheses. Very important that I do that right, especially on this one because -3 and inside of the parentheses, -3 times -3 gives me a +9. On the right-hand side, I get a -9. Now, +9 is a different number than -9, obviously. And so that's a false statement. And therefore, that ordered pair, -3, -3, is not in the relation. Let's take a look at 12, -6. Well, again, -6 is the y value, so make sure you put that in for the y value inside of parentheses. -6 squared equaling 3 times the +12. I end up with 36 is equal to 36. That's a true statement. And so that one is in the relation. 12 -6 is in the relation. How about 12 +6? You see where this is going. 6 squared is equal to 3 times 12. Plug in 12 for x, 6 for y. I once again get 36 is equal to 36. So that is also in the relation. 12, 6 is in the relation. Also, 12 -6 is in the relation. By the way, notice what this means. This means this relation could not be a function because 12 gets sent to -6, but also the input of 12 gets sent to a +6. So 12 got sent to two different spots. So this relation, y squared equals 3x, does not represent a function whose inputs are x and whose outputs are y. Now, in general, this is how it goes. So plugging an ordered pair in, if it gives you a false answer, then that ordered pair is not in the relation. If it gives you a true answer, that ordered pair is in the relation. Now, in these two examples, both example 2 and example 3, we found a couple of points that work. But in both of these examples, since we have infinite domains, there are more than just 2 points that work. There's infinitely many points that work in example 2 and infinitely many points that work in example 3. In order to represent those infinitely many points, well, obviously this equation is one way to represent those infinitely many points, those infinitely many ordered pairs. But we can also graph a relation and get a visual of all of the ordered pairs which satisfy the equation. Oftentimes, we can do just that. We can graph a relation. Since a relation is the set of all ordered pairs which satisfy some equation, doesn't always have to be just a single equation, but in this case, we're dealing with single equations. Then each ordered pair can be represented by a point on the Cartesian coordinate system or the rectangular coordinate system. Generally, we write this horizontal line and we call that our x-axis that represents the x values, and the vertical line represents the y values. And so each ordered pair can be plotted out by moving in the x direction, what we need, right goes positive x values, left goes negative x values. And then up is positive y values, down is negative y values. So each ordered pair can be plotted on this plane. If I was going to plot the ordered pair 2, 1, I'd move in the x direction 2 units, and then up 1 unit, and then that point in the Cartesian coordinate system, or Cartesian coordinate plane, or rectangular coordinate system, or rectangular coordinate plane, would be a representation of the ordered pair 2, 1. Therefore, each ordered pair can be plotted on that Cartesian coordinate system. By the way, it's called Cartesian. It might seem like a weird word. That's because it's named after a mathematician named Descartes. So that's where you get the first part of that. And rectangular because you're moving in rectangles, left and right, up and down. So there you go. So let's take a look at a couple of examples here. In fact, let's take a look at the examples we have. X minus 6y equals 10, and y squared equals 3x. Now, there are multiple different options for how to graph this function. If we wanted to do it by hand, what we would do is we'd create a bunch of ordered pairs that worked. We'd say, oh, 4, -1 and 22, 2, we know worked because of our previous examples. This is the same relation that was in our previous examples. Now, 2 points is not going to be enough to establish a pattern, but what you could do is you could start plugging in lots of different values. Maybe I plug in a certain value for y. Let's say I plug in a 0 for y, and I ask what numerical value for 10 would make this a true statement. And what I could do is say, well, x minus 6 times 0 equals 10, and then simplify that and say, if I plugged in 0 for y, then x would have needed to have been 10. So now I can see that the point 10, 0 works. I could do that for any value of y that I wanted. If I plugged in a positive 1, what would happen is I'd get x minus 6 is equal to 10. That means x would have to be 16. So the point 16, 1 would have also been an ordered pair that worked. Now I just plugged in for y in a couple of different spots. You could have also just as easily plugged in values for x. Maybe I plug in an x of 2 and then solve. I'd have to subtract 2 from each side. I get -6. Y equals 8. And that means y would be equal to a -8/6, which is -4/3. So the ordered pair 2, -4/3 would have also been a point that's a solution. And you could have plugged in whatever x values you want. So just plugging in an x value, solving for y, plugging in a y value, solving for x. You could do that as many times as you wanted and get as many points as you wanted. And then you plot those points on the Cartesian coordinate system and you'd establish a pattern. Let's do that for this. So I'm going to I'm screen sharing, so I'm going to utilize the Desmos calculator just to make it look a little bit nicer. Obviously, if I'm plotting the point 4, -1, I go to the right 4 units and then down 1. I get this point right here. Let me just turn that on, that point. And then 22, 2 would be way out to the right. 22 and then up 2. It'd be this point right here. 10, 0, it'd be 10 to the right, and then 0 up and down means it's on the x-axis. So I get that point. 16, comma 1 is this point right here. Turn that on. And then 2, -4/3 is somewhere about right here. And we get this pattern of dots. This pattern of dots, as you can see, looks like a straight line. In fact, it is in a straight line. So not only are these ordered pairs going to work, but every ordered pair on this line is going to work, this straight line here. In Desmos, you can actually not even do the plotting of points. You can actually just type in the equation and it will give you the graph of that equation. So without even seeing that, this is the straight line. And then not only are these 5 points going to be in the relation, but every ordered pair on this line is going to make that equation true, and therefore every ordered pair is going to be in that relation. So this is the graph of x minus 6y equals 10. Now we could do the same thing for y squared equals 3x, but just for the sake of time, let's utilize this technology, Desmos, to graph y squared equals 3x. We get this shape. And remember, two of our points that were on that line, I guess I can use these. Two of the points that were on that line were 12, comma 6 and 12, comma -6 from earlier. We get this point and we get this point. So this is the graph in black of all points which satisfy the equation y squared equals 3x. Again, on Desmos, you can graph it by just typing in y squared equals 3x. I'll probably I'll show you a way to do graphing on the TI-84 a little bit later, or maybe in a companion video to this one. But there you go. Now we have the graph of y squared equals 3x. That is the set of all ordered pairs that make that equation true. So like I said, you can graph by plotting a bunch of points and getting a pattern and then kind of connecting the dots. You could have done that with the y squared equals 3x as well, but I didn't want to take all the time to plot a bunch of points with that one. Or you could just plug in the equation into some technology like Desmos or the graphing calculator. If you do this with the graphing calculator, you need to be aware of a couple of things. But again, I won't go over that on this video. Now, those two equations represented relations. If we have a function, another notation that we will have is called the function notation. That is f and then a parentheses x is equal to an expression. Now, f, this letter, doesn't always have to be the letter f. The most common letter we use for functions is f because obviously that starts with the word function starts with the letter f. But also common other function letters are G and H. So we have a function of x is equal to an expression. What this is saying, linguistically, we say f of x is equal to that expression. The variable x is still the input. The f of x, which is equal to the expression, is the output. And we find the output by plugging in the number into the expression. So if we do have a function where x is the input and f of x is the output, we can write the function in this way. F of x is equal to some expression. Let's do an example. Let's take the function f of x is equal to 7x minus 2. And we'll find the output values f of 2, f of negative 4, f of 0, and f of 11. This is saying when you input a 2, what into the function, so that's the notation. F of 2 means you're inputting 2 into the function, and we're asking what do we get out? So f of 2 is going to give us out a 7 multiplied times 2 minus 2, which as we simplify that, we get, let me rewrite this, f of 2 is equal to, that'd be 14 minus 2, which is 12. So f of 2 is equal to 12. And that means the ordered pair two comma 12 is a part of this relation. And I could graph 2 comma 12 and see where that is in my Cartesian coordinate plane. Let's look at f of negative 4. If I wanted to input a negative 4 into my function, the output is going to be 7 times negative 4 minus 2. And that means f of negative 4 gives an output that would be negative 28 minus 2, that's negative 30. And once again, that means in our notation that we had earlier that the ordered pair negative 4 comma negative 30 is in the graph of that function. F of 0, well, f of 0 gives me 7 times 0 minus 2. Get cursor out of the way. And therefore, when we input 0 into my function f, we get out a negative 2. That means the ordered pair 0, negative 2 is a point that gives me a true statement for the function. If I input an 11, I get 7 multiplied times 11 minus 2. This is a bit overkill, obviously. But we see what's going on. 77 minus 2 gives me a 75. And we have the ordered pair 11, 75. That is another ordered pair in the graph of my function. So we can put in any input values that we want. I just use integer input values in this case. And my expression was 7x minus 2. Obviously, the expressions can get more complicated. The inputs don't always have to be integers. And we can get lots and lots of other stuff. Let's do just that. Let's use some different input values and let's use some more complicated expressions. Not that it's super complicated, but let's take h of x is equal to x squared plus 2x minus 9. Our function here we're calling h now. And let's find the following output values. H of negative 4, h of 2.3, h of negative 6, and h of 2. All right, so I will do this pretty quick. Hopefully we have a good idea of what's going to come. When I input a negative 4 in for my x value, I have to take negative 4, square it, plus 2 times negative 4. In other words, I have to make sure that every x value gets replaced with a negative 4. That, after I do that, then minus 9. And I'm just going to write this on one line here. So h of negative 4 becomes, that's going to be 16 minus 8 minus 9, which is a negative 1. So when you input a negative 4, your output is negative 1. And again, that would mean the ordered pair negative 4, negative 1 is on the graph. We can do that for any value for x. So x doesn't need to be an integer. We can take 2.3 squared plus 2 multiplied times 2.3 and then subtract 9. When you do that, type this into your calculator, or I guess you could do it by hand, but it's a lot easier to type into the calculator. I got a decimal of 0.89 as my output. That is 0.89, or just 0.89, whichever you like to write. When you input a negative 6, again, inputting a negative 6, make sure that negative goes inside the parentheses. So negative 6 squared plus 2 times negative 6 minus 9 becomes a 15. When we input a 2, we get 2 squared plus 2 times 2 minus 9, and that becomes a negative 1. So we get the ordered pair negative 6, 15, the ordered pair 2, negative 1, also the ordered pair negative 4, negative 1. Remember, that's perfectly fine. That still is a function. We can have, as long as my input has one single output associated with it, we're good to go. But if I have two inputs with the same output, that's perfectly fine as a function. So this one is in function notation, so it's guaranteed to be a function. But that's the idea of finding these output values. Now we can do the reverse as well. So we can take my original function notation f of x equals 7x minus 2, and we can find input values which give us specific output values. You can phrase this in a couple of different ways. You can say, what is x if f of x equals 12? You can say, what is x when f of x is equal to negative 31? You can also say, find x when f of x is equal to negative 31, or find x if f of x equals 12. So there's a number of different ways to phrase it, but in the end, you're finding an input value given that you know the output value is a specific number. If we're trying to do that, if we're trying to find an input value which gives us a specific output value, then we know that the output is this expression. When that expression is equal to 12, we can find our input by solving for x. So in other words, all we have to do is set this expression equal to 12 and then solve for x. I would add 2 to both sides, which would give me 7x is equal to 14. Then I divide both sides by 7. That would give me x equals 2. So when the input is 2, then I get an output of 12. And you can check this by plugging in and setting f of 2, or plugging in f of 2 and seeing what you get. The same thing is true with a negative 31. I would just have to take 7x minus 2, set that equal to negative 31. When I add 2 to both sides, I get 7x is equal to negative 29. And then I divide both sides by 7. Now, 29 divided by 7 as a decimal gets me an ugly decimal. As a fraction, it's just going to be negative 29 over 7. If I'm dealing with an improper fraction. You can also say that's negative 4 1/7 if you want to do a mixed number. It doesn't really matter. The point is, you solve for x, obviously I get a fraction in this case. So that's how we can find input values if we're given output values. So this was one way to phrase this in example 7. What is x when, or what is x if my function is this? You can also phrase it this way. Let's take a new function. G of x is equal to negative 3x plus 42. And say if g of x is equal to 12, what is x? Or if g of x is equal to negative 31, find x. Again, lots of different ways to phrase these. Just like before, I have to recognize that I'm given an output value, in this case of 12, and my output of the function is the expression negative 3x plus 42. So negative 3x plus 42 is equal to 12. I would subtract 42 from both sides. That would give me negative 3x is equal to negative 30. And then I would divide both sides by negative 3. That would give me x is equal to 10. So when x is equal to 10, the output will be a 12. Again, notice that this is a different function, so I should have expected different inputs to give me the output of 12. Negative 31 is my output. Well, if I want to find the input that gives me the output of negative 31, I just set negative 3x plus 42 equals to negative 31. Then I would subtract both sides by 42. The left-hand side then would become negative 3x. The right-hand side would become negative 73. Dividing both sides by a negative 3 gives me either 24 and a third, or as a mixed, as an improper fraction, 73 over 3. So as an improper fraction, it'd be 73 over 3. As a mixed number, it would be 24 and a third. Doesn't matter which one you write it. I tend to use the improper fractions because they're easier to deal with algebraically in most instances. But there you go. Now we could have done this with our function that had an x squared on it. This one as well. We could have said, well, when is this equal to 15? And then we could have set x squared plus 2x minus 9 equal to 15. That, though, would require a little bit more advanced solving techniques that we'll see later on in this course. So we won't do, I won't have you, at least not at this stage, solve something like x squared plus 2x minus 9 equals, again, 15. I guess let's do 12. Because we'll do that sort of solving technique later on in the course. So, but just know you could have done this with any function. You could have said, if this has an output value of 12, what is the correct x value that you plug in? Or if this has an output value of -1, what's the x value you need to plug in? And you could say, well, actually, there's a couple of them. There's -4 or 2. Both of those, when you input those, give an output value of -1. But like I said, we'll stick to pretty straightforward functions so that the equations are nice to solve in this section. Something like -3x plus 42 is equal to a number, or 7x minus 2 is equal to a number. And in these, when we had x squared plus 2x minus 9 is equal to a number, well, we'll look at those later on in the course. Now, this brings up the question, when can an equation be turned into a function? We said that any equation gives us a relation between x and y values. So if I want a function, and specifically, if I want a function such that y is a function of x, so that I can replace the y with an f of x, how can I tell when an equation will give me that? How can I tell when I have y as a function of x, where x is the domain and y is the range variable? So x is the domain variable, y is the range variable. Well, the first way I can do it, if I want y to be a function of x, and I know my function notation is f of x is equal to an expression in the variable x. If I can rewrite my equation to look like y is equal to the expression in x, then I know y can be thought of as a function of x. In other words, if I can get y by itself on one side of the equation, and on the other side of the equation, I can get an expression in x, then algebraically, I know that y is a function of x. I know the y and the f of x are basically doing the same thing, are doing the same roles. So let's take a look at this relation that we saw earlier, x minus 6y equals 10. Let's determine if this relation represents a function with x as the independent variable, that means input variable, and y as the dependent variable, that means the output variable. So independent means input, dependent means output. So what I would do algebraically is try to solve this equation for y. So I want to get the y by itself on one side of the equation, and on the other side of the equation, I just have a single expression with respect to x. In this case, the first thing I would do is I would subtract x from both sides. If I do that, I get on the left-hand side, if I subtract x, I just get negative 6y left. On the right-hand side, I'd get minus x plus 10, or you could say 10 minus x on the right-hand side. Then, in order to get y by itself, I would divide both sides by a negative 6. So I'd take the negative x plus 10 and divide it by a negative 6. Now, we can divide each of those numbers by a negative 6 if you'd like. Doesn't really matter at this stage what you write, but it does matter what you write, excuse me, but there's multiple ways of writing it. That's what I should say. There's multiple ways of writing it. 10 divided by a negative 6 is -1 2/3, which as an improper fraction is -5/3. Obviously, -1 divided by -6 is 1/6. So whether you write your expression this way, y equals -x plus 10 all divided by -6, or whether you write your expression as y equals 1/6 x minus 5/3, I have y equals a single expression in terms of x, and therefore that is going to be a function, because I could have also written that as f of x equals 1/6 times x minus 5/3. So now I know this relation is a function. All right. Again, is a function with x as the input variable and y as the output variable. And that's what we're looking for. So algebraically, if I can get y is equal to a single expression in terms of x, then I know I have a function, and f of x and y are really performing the same roles. Let's do the other equation that we were dealing with earlier. Y squared equals 3 times x. We saw a graph of that. We found some ordered pairs that work for that. Let's see if algebraically we can show that this is a function where y is a function of x, or if we can show it's not. Now, here's the deal. In this case, y squared is equal to 3x. We may think, well, let's solve for y by taking a square root of both sides. But it turns out if I just take a square root of 3x, I don't get the same thing, because if I'd input a negative or a positive y and then squared it, I would have ended up the same thing. So if I wanted to solve for y, then y would have to be either the positive or the negative version of the square root of 3x. That is not a single expression. That's actually two different expressions. So y is equal to the positive version of the square root of 3x is one expression. Y is equal to the negative version of the square root of 3x is another expression. So algebraically, this shows y is not a function of x because y is not a single expression in terms of x. So this shows that this equation is a relation, but is not a function. So not a function. All right. Whereas the previous one, we'd have that this relation is a function. So we got y equals a single expression in this one, so the relation was a function. In this one, we got y is equal to maybe two expressions, so that means the equation is not a function. If you remember way back in example 3, we actually had said that as well, because we saw the point 12, -6, and the point 12 comma positive 6 were both in this relation, and if the same input value has two different output values, then obviously we don't have a function. So we saw that this wasn't going to be a function. Now we've confirmed it using the algebraic solving technique. Let's take a look at a couple of other examples. Let's see if each relation represents a function with x as the independent, y as the dependent, meaning y is a function of x. Does each of these equations represent a function with y as a function of x? So can I solve for y uniquely? Well, in this first one, what I would do is I would subtract x to the third from both sides, and then I'd divide by 4. So let's subtract first. We get 4y squared is equal to negative x to the third plus 16. And then I would divide everything by a 4. I'd get y squared is equal to negative x to the third plus 16 divided by 4. And then I have a y squared. So again, in order to take a square root, we'd have to do a plus and a minus version of the square root if I wanted it to work. And it's going to be an ugly square root, but that's besides the point. You could rewrite this. Let me actually rewrite this. Doesn't. So I get negative 1/4 times x to the third plus 4. But the real trouble is this two options, one for the plus option and one for the minus option. So we'd say y is not a function of x for that first one. So square roots don't work very well because we have the plus minus options. When I have a squared on my y, it doesn't work very well because of the plus minus options. What if I had a y to the third? Well, if I had a y to the third, I'm going to take a cube root or a 1/3 power on both the right and the left-hand side. So if I did that, it turns out cube roots are perfectly fine to take. And I don't need a plus or a minus out front because if I take a negative times a negative times a negative, I get a negative. If I take a positive times a positive times a positive, I get a positive. So with cube root, I don't need a plus minus there. And therefore, y is a single expression in terms of x. So y is a function of x in this case. Again, the squares force me to do plus and minus. Any even power does that. If I had y to the fourth, I'd have to do a plus minus. But any odd power, when I take a root here, cube root, does not require me to do that. So with a cube root, y is a function of x. What about this one? Well, in short, I cannot solve for y. Since I can't solve for y is not a function of x. There's no y involved here, so I can't solve for y when I have x equals 4. So that one is not a function of x. So be careful with that. Can't deal with squareds on our y's, generally speaking, but generally speaking, we can deal with cubes on the y's. Now, doing that algebraically can take some time and can take some effort. We can do a very similar thing graphically as well. We can determine when an equation is a function using the graph of that equation. We want to see if y is a function of x. That means I want to avoid pairs of points with the same inputs and different outputs. If you graph A comma B and A comma C, where B and C are different, then they are going to appear on the same vertical line. So if you look at the graph of a function and you see 2 or more points on the same vertical line, that if you graph an equation and you see 2 or more points are on the same vertical line, you know that equation is not a function. This is the vertical line test. All right. If we graph our function and a vertical line passes through 2 points on the graph of that relation, I should say. Let me change that. So I changed the language here. If a vertical line passes through 2 points on the graph of a relation, then the graph is not the graph of a function. So that relation is not a function. If every vertical line passes through at most 1 point, could pass through 0 points, but if it passes through at most 1 point of the graph, then the graph is the graph of a function. Now, one other thing is known as one other concept is something called a one-to-one function. A one-to-one function is a function which avoids pairs of points with different inputs and the same outputs. So graphically, a one-to-one function is one where you don't have points on the same horizontal line. Let's take a look at some graphs of functions and determine if, well, let me say, let's graph each equation. Let's determine if that equation gives us a function, and then let's determine if that equation gives us a one-to-one function. So function is determined by a vertical line test. One-to-one would be determined by a horizontal line test. Let's start with x minus 6y equals 10, and then I'll transition quickly to y squared equals 3x. I'm choosing these right now because of the fact that I already graphed them earlier. So here we have x minus 6y equals 10. And we see that it's a straight line. There's let me restate this. At every vertical line here, we only pass through the graph one time. So if I drew a vertical line, notice my vertical line only crosses this graph at one spot. And every vertical line has that property. No matter where I move a vertical line, it only crosses this graph at one point, one and only one point. So this passes the vertical line test, and therefore x minus 6y equals 10 is a function. Now you can also do that with a horizontal line. So if I take, for instance, y equals 0, that's a horizontal line. But also y equals -3 is a horizontal line. And you can see that every time you move a horizontal line, it also passes through at one particular point. So this x equals, excuse me, x minus 6y equals 10, that graph represents the graph of a function, and in particular, it represents the graph of a one-to-one function. Now let's take a look at y squared equals 3x, which we know from before is not a function. Well, how can I tell it's not a function graphically? I can tell it's not a function graphically because as you scroll or as you create vertical lines passing through, you end up crossing at multiple points. For instance, we got 12, 6, 12, -6. Those are 2 points on the same vertical line. And therefore, this y squared equals 3x, we can see is not a function graphically. We already found that out algebraically, but now we can see that that is true graphically as well. And graphically usually goes a little bit quicker because it's more of a visual, quick process. You just say, can I draw a vertical line going through 2 points? If I can, it's not a function. If every vertical line goes through at one or more or one or fewer points, then it is a function. Let's look at these other expressions graphically as well. And we'll quickly decide if they are functions and then one-to-one functions if they are functions. These are also ones I've done algebraically on a previous slide. So we can confirm our results that way as well. So let's do these three. X to the third plus 4 times y squared equals 16. Then y to the third equals 5x plus 7. And then x equals 4. Now, I've typed all of these into Desmos just to save time, but you can do this in a lot of other ways as well. Notice that here, this one is the x to the third plus 4y squared equals 16. Obviously, there's a lot of different places I can draw a vertical line and touch this graph at 2 points. So It doesn't over here if the vertical line is above, if it's here at about 10.3. But as we get into any of these negative values, we're crossing over at multiple places. So there we go. So x to the third plus 4y squared equals 16 is not a function. How about y to the third equals 5x plus 7? Well, if I graph it, I get this shape. And it might look like this goes kind of vertical, but if you zoom in enough, you'll see that you never quite get perfectly vertical. So no matter what line you're actually technically only crossing at one spot. I know that might be hard to see there, but you only cross at one spot no matter where you're at. So that one is a function. Got a little curve to it, but it is a function. Now this one happens to also be one-to-one because if we draw a horizontal line, it also crosses at only one spot. So this is both a function and also a one-to-one function. Now the last equation that we had was x equals 4. Notice that there's an obvious vertical line that goes through infinitely many points. And so this fails the vertical line test because 4, 0 and 4, 5 and 4, 4 and 4, 3 and 4, 2 and 4, 1 and everything in between are all points on that vertical line x equals 4. So this fails the vertical line test, and therefore x equals 4 is not a function. And so each one of these is, through graphing, giving us the same result as we had before. X minus 6y equals 10 is a function. It is also, now we can see, one-to-one. Y squared equals 3x is not a function. X squared plus 4y squared equals 16 was not a function. Y to the third equals 5x plus 7 is a function, and it is also one-to-one. X equals 4 is not a function. Here we were given the equations for all of these relations, but obviously you could do this if you just had the graphs as well. So let's determine if each graph is the graph of a function by using that vertical line test. And then let's decide if it's one-to-one. So we have two pictures here. The one on the left is not a function because you could draw a vertical line. I'll just draw it on here at a lot of different places and go through 2 points. This graph on the right, no matter where I draw my vertical line, whoops, that's not very vertical. No matter where I draw my vertical line, it only goes through 1 point. There is a little bit of curve here that you're not seeing. So this is a function. The one on the right is a function. The one on the left is not a function. The one on the right, however, is not one-to-one because If you draw a horizontal line, it goes through the graph in two spots. Well, not every horizontal line, but there are some horizontal lines that go through the graph in two spots. So this is a function on the right, but it is not one-to-one. On the left, it is not a function. So the one on the right is a function, but not one-to-one. On the left, it is not a function. Let's look at another pair of examples. Here we have two graphs. If you draw vertical lines through the graph on the left, then each vertical line is only going to hit at one spot. So the graph on the left is a function. However, it is not one-to-one because there are horizontal lines that can go through the graph at two or more places. So this graph on the left is a function, but not one-to-one. The graph on the right is also a function. Every time you draw a vertical line, it goes through the graph at one spot. But also, it's one-to-one because if you draw any horizontal line through this graph, it only crosses the graph at one point. So the graph on the left is a function which is not one-to-one. The graph on the right is a function which is one-to-one. Let's take a look at another pair of examples. Let's start with the one on the left. If I look at this graph on the left, every time you draw a vertical line, it crosses through at one spot. If you draw a vertical line right through the x equals 1 value, this one's filled in, this one is not, so you only cross at one spot there as well. So this one is a function, this one on the left. Is it one-to-one? Well, if you draw a horizontal line, it only passes through one spot if I'm down here. If I'm between -1 and 0 and I draw a horizontal line, I might pass through 0 spots, but that's okay. It's not more than one. Anywhere above 0, the y value of 0, I only cross through one spot as well. So the one on the left, even though it has a little gap in here, it's still a function and it is still one-to-one because it passes the vertical line test, so therefore it's a function, and then it passes the horizontal line test, so therefore it's one-to-one. The graph on the right is not one-to-one, and it's all, well, I should say, I misspoke. The graph on the right is not a function, excuse me. The graph on the right is not a function because there's lots of vertical lines you can draw that go through the graph at two or more spots. So on the left, it's a function which is one-to-one. On the right, it's not a function. In example 14, we had a one-to-one function on the right, a function which was not one-to-one on the left. In example 13, we had a function that was not one-to-one on the right, and on the left, we had something that was not a function. That's how I can use the vertical line test and the horizontal line test to see if, first, the graph represents a function. That's the vertical line test. And second, to see if the graph is one-to-one, or if the function was one-to-one, that would be the horizontal line test. So vertical line test tests for functions. Horizontal line tests for one-to-one. So that's the basic idea of how to find functions, how to use function notation, how to use ordered pair notation, and how to determine if graphs and equations represent functions or not.